This segment of nuclear chemistry will cover the belt of stability and radioactive series. Our learning targets include being able to determine the type of decay a radioactive nuclide is likely to undergo and writing balanced nuclear equations to reach the stable isotope in a radioactive series. Let's begin by taking a look at this graph. This graph is known as the belt of stability, also called the band of stability. On the x-axis, you'll notice that we have protons, represented by the letter capital Z, and on the y-axis, we have neutrons, represented by capital N. Take a look at the solid line. The solid line going through the graph represents the ratio of neutrons to protons as 1:1. So you'll notice neutrons over protons equals 1. The dots in the middle of the graph represent stable, non-radioactive isotopes. Notice how the dots, or the belt, ends at bismuth 209. Bismuth 209 was once thought to be the most stable isotope, but actually, quite recently, in 2003, scientists found that bismuth 209 actually does undergo radioactive decay, specifically alpha decay. However, it is stable in that its half-life is very long. It is 19 quintillion years, approximately. Now, notice alpha decay appears at the top of the belt. So alpha decay is likely to occur in nuclei with 84 protons or more, because those nuclei are then considered radioactive. The type of radioactive decay a radionuclide undergoes depends on the ratio of the neutrons to the protons. If we are located above the belt or above the band of stability in this region of the graph, that means that the number of neutrons is very high compared to the number of protons. So for that reason, nuclides in this section above the belt will undergo beta emission. So when the ratio is greater than 1.5 neutrons to 1 proton, then that nuclide will most likely undergo beta emission to reduce the number of neutrons. During beta emission, recall that a neutron releases a beta particle and turns into a proton. Below the belt of stability, particles or nuclides will undergo positron emission or electron capture. In this region, nuclides typically have a low neutron to proton ratio. So there's an abundance of protons. In order to decrease the number of protons, the nuclide will emit either a positron or it'll undergo an electron capture. And in doing either of those two processes, the proton will convert into a neutron. If the atomic number of the radionuclide is greater than or equal to 84, the nucleus will undergo an alpha emission. Take a look at this other graph representing the belt of stability. There are a few more colors on this graph for us to examine. The black dots, though, still represent stable isotopes. Now, when we say stable isotopes, that means that the half-life of these isotopes is longer than 46 billion years, which is approximately 10 times the age of the Earth. So they are around for a very, very long time. Now, notice the colors surrounding the black dots. There's red, yellow, green, and blue, as well as purple. So there's a key at the top of the graph showing you the half-life of each of these isotopes. So you'll notice that the red dots, those represent isotopes with very long half-lives, or the more stable isotopes. Down at the bottom here of this key, you can see the blue dots have the lowest half-life. They're predicted to last less than 1 second. And notice their distance from the band of stability. The further away the colors are from the black dots, the progressively less stable they become, the more radioactive they are. So if you were to rank the colors, we would say red is the most stable of all of these colors, then yellow, then green, then blue. The purple dots represent isotopes that are super heavy nuclei. They are predicted to be relatively stable. Notice the location of the purple dots. Here they're called the island of stability. So these purple dots show nuclides that have a high number of protons and a high number of neutrons. These are very heavy nuclei. In many cases, these elements have not been observed or synthesized, so they are predicted to be relatively stable. This is another view of the belt of stability zoomed in. So you can see the black dots appear again, and the black dots still represent stable isotopes. The type of radioactive decay a radionuclide undergoes depends on the ratio of neutrons to protons. So in this picture, we're looking at the change of a radioactive isotope. So in this case, the parent isotope, the unstable isotope, the change it undergoes to become the more stable daughter nuclide. So if you look at each of the circles, they're color-coded. The red circles represent alpha emitters. So remember, an alpha particle is a helium nucleus, mass number 4, atomic number 2. It is the most massive form of radiation. And when an alpha particle is released, there is the most dramatic change in the number of protons and neutrons. Notice the red dot with the arrow. If you look at its position to start and then look at its position when it becomes stable, represented by this black dot, you'll notice that to reach this position, the number of neutrons was reduced by 2 because we went down the y-axis, and the number of protons was also decreased by 2 because we went from right to left 2 places. So when a particle undergoes an alpha emission, a nucleus undergoes an alpha emission, it's going to make the most dramatic jump on the belt of stability because it involves the greatest loss of subatomic particles. A beta emission is represented by the blue circles. And remember, a beta emission is occurs when we have an excess number of neutrons. So a beta particle is released and the neutron then changes into a proton. So if you look at the blue particle with the arrow next to it, notice it only moves one position or one spot because it goes down. The number of neutrons goes down by 1, but it increases in proton number because the position shifts diagonally and also to the right. A positron emission, as well as an electron capture, is likely to occur when there is an excess number of protons. So to reduce the number of protons, the radionuclide will either absorb or consume an electron from the electron cloud, or it will release a positron to change the proton into a neutron. So notice the yellow circles are moving diagonally up and to the left, and that shows that the number of protons decreases by 1, and then the number of neutrons also increases by 1 by this change in position here. This is a graph representing what we call a radioactive series. Some nuclei cannot gain stability by a single emission. For example, uranium-238 needs to undergo several alpha decay steps shown using the orange arrows, and several beta decay steps shown using the teal arrows to gain stability. the decay will continue until a stable nucleus is formed. So in this case, the stable nucleus is lead-206 at the bottom here. This series of multiple nuclear reactions, beginning with an unstable nucleus and ending with a stable one, is called a radioactive series or nuclear disintegration series. Let's try to write equations in a radioactive series together. So we're going to use the same example from the previous slide, the decay of uranium-238, as it continues to decay to form the stable lead-206 isotope. So we already saw in the graph that there were several steps involving alpha and beta emissions to form polonium-214, which is one of the intermediate nuclides. So we are going to write out the last 4 reactions of the decay series where polonium-214 undergoes an alpha emission. So that'll be our first reaction that we write. A beta emission, that'll be our second reaction that we record. And then another beta emission, that'll be our third one. And then a final alpha emission. So these are our 4 reactions that we will write together. Let's start with polonium-214. So our first reaction is polonium. Its mass number is 214. So you want to make sure you have your periodic table handy so you can look up the atomic numbers for each of these elements. Polonium's atomic number is 84. And the first equation has us undergoing an alpha emission. So we're going to draw an arrow. The alpha particle is 4, 2. 4 is the mass number, 2 is the atomic number, helium nucleus, plus the resulting daughter isotope from this first reaction. So remember to make sure the sum of the numbers on either side of the arrow is equal. So 210 would be the mass number for this isotope. 210 plus 4 gives us 214. And at the bottom, we'll have 82 as our atomic number. 82 plus 2 will give us 84. So use 82 to look up the identity of the daughter isotope. Hopefully you can see that it's lead, Pb. Now we're going to move on to the second reaction, the second nuclear equation. It is going to be a beta emission. So for this equation, we are going to use the daughter nuclide from the first reaction. So this is the daughter nuclide, and we're going to take this and copy it into the position of where the parent should go. So the daughter becomes the parent. So lead still has 210 as its mass. We're just copying it exactly. 82 is the atomic number. It's going to undergo a beta emission. So we're going to draw an arrow and draw our beta particle, mass number of 0, charge of -1, symbolized with an E, lowercase e, plus the mass number is going to remain unchanged, still 210. And then the bottom number is going to be 83 because 83 minus 1 will give you 82. Use your periodic table to look up the identity of element atomic number 83. So that would be bismuth. Now we're going to take bismuth and have it begin the third nuclear decay reaction. So bismuth, mass number 210, atomic number 83, will undergo a beta emission. So we're on the third equation, another beta emission. So just go ahead and write down your beta particle, and then the resulting daughter nuclide mass number will still be 210. It remains unchanged, and the bottom number is going to be 84, the atomic number. Look up 84 on the periodic table, and you'll find that it is polonium. PO, capital P-O. So it looks like we're back to the original polonium, but actually if you take a closer look, the mass numbers are different. So this is a different isotope of polonium. We're going to use polonium here to begin our fourth and final step. This nuclide will undergo an alpha emission. See the directions, final alpha emission. So we're going to draw our alpha particle, helium nucleus, remember? And fill in the blanks for our daughter isotope. So 206 at the top, 206 plus 4 gives us 210. And then at the bottom, we'll have 82. Use 82 to look up your element symbol. 82 belongs to lead. Lead 206 is then our final stable daughter nuclide. Let's try one more example. Complete the decay series of nihonium, NH278, that underwent 5 alpha decays to become lawrencium 258. To finish the series, lawrencium 258 undergoes an alpha emission. So these are the steps that we're actually going to record. Alpha emission, that's our first equation. Electron capture, that'll be our second equation. And then a final alpha emission. Our last equation will be an alpha emission. So there's only 3 steps. Show the reaction to reach the final daughter isotope for nihonium 278. So let's start with our first equation. Lawrencium 258, that's our mass number. Take a look at your periodic table to find the atomic number of lawrencium. It is 103. This is going to undergo an alpha emission. So arrow, draw your arrow, and then your alpha particle, helium nucleus. Okay, fill in the blanks for your daughter isotope. So 254 at the top, 254 plus 4 gives you 258. And then at the bottom, we have 101. Next to that, we're going to write our element symbol. So go ahead and look up 101 on the periodic table. And that atomic number belongs to mendelevium. So we are on our second reaction now. Our second nuclear equation starts with the daughter isotope from the first reaction. So mendelevium 254, atomic number 101. It's going to undergo an electron capture. This is our second equation. So remember, an electron capture is when an electron is consumed by the nucleus. So the electron will appear before the arrow. So the mass of an electron is 0. The charge of an electron is -1. On the product side, for our daughter nuclide, we'll still have the same mass at the top. The mass will remain unchanged, 254. But at the bottom, 100 minus 1 gives us, 101 minus 1 gives us 100. So take a moment, look it up on your periodic table. 100 belongs to fermium, FM. So now we're on our final nuclear reaction for this series. The mass number goes at the top. The atomic number goes at the bottom. This is undergoing an alpha emission. So we're going to draw an arrow. And just like the first step, our alpha particle is listed, and then fill in the blanks for the mass number. 250 plus 4 will give us 254. And then at the bottom, 98 plus 2 will give us 100. So use your periodic table, look up 98. That atomic number belongs to californium. So californium then is the final daughter isotope.